Oi, 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 sim. Good morning to everybody. Welcome to Rio. Welcome to IMPA. It's a great pleasure to have you here, to welcome you today as we celebrate our partnership with the Italian Dynamical System Network, DinAmicI. We hope this meeting will foster new collaborations and lead to fruitful research partnerships. We would especially thank José and especially Leticia Hibes and Sueli Limas, who worked a lot in the last months for making this meeting possible. And no conference is possible without financial support. So we really deeply thank the agency that made this possible, CAPES, CNPq, Insight Mati, and FAPERGI. And we thank a lot also IMPA, who hosts this meeting, and that actually also became part of the, basically became a financial agency, because also offered financial support. But we in particular thank all of you for being here, and I hope you will have a very nice week and a very nice conference.
Ciao. We forgot to thank the Italians. You know that we also have some support from the Italian part, and this comes from Alfonso Sorrentino from Roma Tor Vergata, and also by Marco Lenci, he is one of the professors in Bologna, University of Bologna, okay? Sorry, just to compliment what Luna said.
And so let's start. It's my great pleasure to start this conference introducing Stefano Marmi from Scuola Normale Superiore di Pisa, who will speak about deterministic and random dynamical systems and systemic risk in finance. Stefano?
Okay, so is it working? Yes. Okay, cool, thanks. So first of all, thank you for inviting me. And it's always a great pleasure to be in Rio and to be at IMPA. And also I have a lot of nice memories here, so thanks a lot for bringing all of us here. So what I want to do today is to introduce you to a class of models which I think are interesting and not very much investigated. And these models arise from problems in finance. I'm not sure that I will excite your mathematical side enough. I hope so. But in order to try to leave you with a little bit of interest, in the subject, I decided to spend the first 3-4 slides by just introducing what I'm going to talk about. Then I will have a certain amount of time devoted to motivating it and explaining why it arises from an unconventional setting and gives rise to this unconventional model, because the model per se is a very, very simple one which has been studied by a lot of people. It's basically an interval map with noise, with additive noise. But the property which is interesting of this noise is that the noise is position dependent, okay? So you have a variable, a noisy variable y t minus 1, some what people call innovations in econometrics, which may be a Gaussian variable or a uniform variable, IAD, etc. But the variance in front of this, say normalized, is going to be dependent on the position. So you have a deterministic map, a noisy deterministic map. And this fact that the noise depends on the position is what makes the analysis of this model a little bit different from usual. People call this kind of situation heteroscedastic in statistics and in econometrics, basically it is way more impressive than saying position dependent, heteroscedastic. And the point is that these kind of models don't appear very often with this position dependence in the literature, but they're not strange. They're not strange. So, of course, there is a separation of time scales. So there is a parameter, keep it in mind, boldface n or blackboard n, little n, which is basically an integer which exprimes which will be related to the fact that you have two time scales, one for the deterministic map and one for the noise, which will arise from some sort of fast random system. So 1 over n is a fast to slow time scale ratio, which we imagine to be very small, or if you want little n to be very large. And in general, problems where you have two separated timescales are plentiful in science. You have a lot of examples in physics, in chemistry, in biology, in neurosciences. I mean, it's an infinite list of systems. And in many cases, you can also think, it's not unnatural to think that the slow system is actually deterministic, because sometimes it comes out from some sort of averaging, as it's common in statistical mechanics. So you may have a deterministic model which is a sort of average, and then you want to understand the influence of noise on that. But what is a little bit unconventional is that I will try to explain you why this is a natural setting for some of the most interesting open problems in finance, in particular a problem which goes under the name of systemic risk, which I will try to explain what it is, or at least to give you also an idea of the scale of the problem in a minute. So the dynamics, of course, will be described using a Markov chain. We will study the noisy regime for finite n and the deterministic limit when n goes to infinity. I forgot to mention, but all what I'm going to say has been made together with Fabrizio Lillo and Giulia Livieri, Anton Solonco, and Sandro Vaienti. And more recently, we have also been working on this topic together with Matteo Tanzi. And also, I hope, and I really would like to get at the end to mention a few things which just started to investigate with Marco Ioffredo, who is a student at the Scuola Normale, he's sitting somewhere there, and who is preparing his master's thesis supervised by Matteo and me. So, I mean, this is just to give credit to all the people. And so the point is that, of course, the setting is very general, it's very important, there is a lot of literature, but that kind of noise we are interested in, to our best knowledge, had not been investigated, probably because there was not that much of reason of thinking about it if you didn't have an underlying model to justify it. In our problems, the map T, you will see later, turns out to be somehow unimodal. So it will be some unimodal map on the interval with a quadratic critical point and negative Schwarzian derivative. And this is all very welcome because, I mean, that's the setting that we like for understanding this. So where do this, okay, finally, I mean, just a few takeover. The rigorous results that we have been able to prove are related to the existence of the stationary measure, and which is obtained by somehow extending a little bit the standard approach. So we have we show that on suitable Banach spaces, the Markov operator associated to the chain is quasi-compact. Actually, one can show that it is compact. And so we get the existence of finitely many bounded variation stationary measures. And we show that one has uniqueness if you have a periodic, an attracting periodic orbit or a topologically transitive attractor. And we show some form of stability, so convergence to the invariant measure. And finally, we also show continuity of the Lyapunov exponent and convergence to the deterministic one in the zero noise limit and the central limit theorem. So if you only want to know about the math and you really don't want to know about anything else, since I'm very bad at explaining proofs, you can basically start sleeping and thinking to what you want. Now I will try to tell you why I think the problem is interesting, how is it related to finance, and how it can also, and in the end I hope I will show you First of all, how it has been applied to a real data set, because that is a little bit the point. We would like also to show that under certain situations, this kind of models which are sort of heretic, because I mean, as you will see in a second why they're heretic, they blow sand in the face of traditional mathematical finance, are actually justified, interesting, and can even explain data sets. So they're not just, or at least, well, we managed to publish claiming that they explain data sets, okay? So I mean, we convinced at least a couple of referees that they explain a data set, okay? Then, of course, what I'm saying is that there is still a lot of work to do, okay? So I don't want to oversell what we did. Now, efficient markets at random walks. So you all know that finance is usually not present in dynamical system conferences because, yes, we do like random dynamics, but we basically come from deterministic dynamics. And deterministic dynamics is not the way people think about finance. People think about finance in terms of diffusion processes, okay? And this is true since the work of Bachelier, who in 1900 studied, introduced the random walk model for studying financial prices and stock options. And it became basically the main thing with the work of Samuelson, because Samuelson somehow proved that when markets are efficient, in a very precise sense, the price, which is the logarithm of the price, which is S, follows a random walk. So you have a diffusion process and a drift. Now, the thing has changed the history of mankind. I mean, this cannot be, it's really an amazing revolution which started. I'm not judging it. You may be pro, you may be against, but it's a fact that it has changed the history of mankind, because basically it provided mathematical tools for building very accurate models or decently accurate models for trading of financial derivatives. Financial derivatives are basically bets, contracts, which allow you to bet on the future price of some underlying, which could be a stock, but it could be a commodity and so on. I mean, talking about commodities, of course, in Brazil, it's a very natural thing. I mean, you're full of commodities, coffee, and it's just to make an example, but plenty of others. And then it turned under some idealized but convenient assumptions of having a market where there is no possibility of arbitrage, where the liquidity is infinite, where you can borrow money from central banks at a fixed interest rate with infinite, I mean, they have infinite amount of money that they can borrow you and so on, and no transaction costs. So all these assumptions are, of course, ideal, I mean, big idealizations, but then basically you turn the problem of understanding financial mathematics into a PDE problem. Okay, PDE problem, moreover, of a relatively nice way, because these are parabolic equations, so they're not the worst that you can get, and they're typically linear or semi-linear. They're not too bad. Okay, so there is a lot of stuff that you can do in this way, and this actually changed the world. This is a picture which I want to show when I talk about this, because it gives you an idea of the growth of the notional amount of derivatives which are traded in the world. The estimate for 2024 is that the notional amount is around $1 quadrillion United States dollars, which is some sort of remarkable figure. Okay, so and this is also what people call the financialization of economics. The fact somehow that finance seems to have tilted the strength of the relation between economics and finance is tilted in favor of finance. Now, systemic risk is related to the fact that somehow there is interconnectedness between the various agents in various ways, either because they trade the same stuff, and so, I mean, if I start to pump some asset, this affects your portfolio, or because there is a lot of mutual lending between banks. I mean, mutual lending, I mean, that's basically the favorite sport of banks. I mean, lending money between one to the other and so on. And what happens is somehow the distress of one agent can actually very quickly propagate in a way which is not really always well understood to other agents. So, I mean, they are not isolated anymore, okay? There is sort of very strong interconnectedness of the risks between the various banks. And the banks themselves, you should keep in mind that in general, the key word for understanding the financial world is leverage. Basically, the ratio between the balance sheets, the assets of all the financial institutions and the equity, which are what you are left when you subtract from your assets or your liabilities, or what you borrowed, this ratio is typically pretty high, of the order of 9, 10 in the good cases. In some cases, in 2007, there were mad banks which were running at around 100. They failed, but I mean, there were things like that. So this kind of ratio, leverage, is very big, and you should think leverage of what the name says. Leverage is you're magnifying your spreads, okay? So you basically want to play the simplest of the games. You want to borrow money for the cheap and lend money for more expensive, but the difference between the borrowing rate and the lending rate is maybe 1 or 2%, which is not that much. But if you put 10 times multiplier in front of it, becomes 10, 20%, and then it starts to be interesting, right? I mean, and then you're happy. So that's basically the logic. And the point, the banks work on fractional reserves. So if we all ask the money back from the bank, we will not get it. It has always been like that. And then, of course, there are various possible contagion or bank runs which can produce instability in the banks. The most, just in 2023, there was a little financial crisis in the United States, not that little, but I mean contained. There were several banks which failed in the span of a few weeks, and relatively mid-sized banks, not small, not huge, but not small. And then, of course, there was a big story of Credit Suisse in Switzerland, okay, which has been bailed out by the Swiss government, forcing UBS to buy it. And in general, these stories are very frequent in the sense that only in the United States, between 2001 and 2024, there were 567 bank failures. And of course, the systemic risk thing became a big argument around 2008, 2009, because as you can see, the financial crisis is very visible on this graph, okay? So on the left, you have the assets of the banks which failed, I mean the total assets, and on the right, in red, you have just the number of bank failures, which peaked in 2010 around 150. Okay, so and when banks fail, especially if they're very big, it's a big thing, because large banks are huge, really huge, okay? So they're not little things. I mean, the asset, by asset, the largest banks are all Chinese, unsurprisingly, and they have asset of the order of 4 or 5 United States dollar trillions. So these are behemoths, okay? So if something like this fails, it's enough basically to tilt the economics of a country, well, of the size of the United States or China, which means the rest of the world. So you cannot underestimate the importance of having a good regulation and of preventing this kind of instabilities. Okay, so the problem of systemic risk has actually been somehow not very much considered in the financial and the economics literature until the financial crisis. There were some investigations, but not so big, especially because in a quite surprising way, most macroeconomic models did not include the financial system. Somehow it's surprising, but that's the way it is. Somehow the financial system was not considered to be essential for understanding macroeconomics. I'm a bit exaggerating. There were actually heretics, mostly post-Keynesian ones, and Hyman Niemiński is an American economist who has been quoted many times for this. And he actually formulated a financial instability hypothesis. Somehow he was exactly, underlying the role of leverage and the role of speculative bubbles in making finance intrinsically unstable. But if you think of finance, if you want to concentrate on finance and a little bit less on economics, the literature is not immense. There are nice attempts of introducing financial instability indicators which were made by Duadi and Young-Na Choi and others. And basically, they had this idea of following the cash streams between the various banks and the various financial institutions, and then somehow introducing a sort of top-Lyapunov exponent. You try to follow these cash streams, you have a product of matrices, and then you try somehow to compute an approximate top-Lyapunov exponent, and then, of course, if this becomes positive, then you are a little bit worried, then you should perhaps do something. So that is, of course, if Raphael were here, he would not be happy. I'm oversimplifying, but I mean, it's just to say that it is maybe inspired by dynamics more than actually producing a dynamical system. And what I want to do here is, on the other hand, show how you can, if you keep into account some of the real features of markets, introduce a class of dynamical systems. We will really have a map and things like that, which somehow encode some elements of the problem. Okay, so, and the variable on which we will focus is the leverage itself. So the leverage, the variable, you should think of the variable that I want to study, the map, the unimodal map of the interval. The variable in the interval will be related somehow to the leverage, okay? So you may ask, well, the leverage, I just said that it is something bigger than 1. Yes, it is. So you can think of taking a variable which is going to be fundamentally something like the leverage minus 1, so that you are back between 0 and plus infinity, and then you will divide by something which is related to max liquidity. So here we are going in a world which is not the ideal world of math finance. So we are assuming that liquidity is not immense, is not infinite. Basically, you cannot print all the money that you want all the time. And then in this way, this becomes a variable. Our variable phi will be a variable of the interval. And then the point is that there is a lot of evidence in financial literature that financial entities work with roughly this idea. They have a target leverage. They want to be as leveraged as possible under the regulation. So the regulator says you cannot do crazy things. But basically, up to some point, okay? So you can be crazy up to some point. You can speculate, you can leverage your portfolio up to some point. And this point has to be estimated on the basis of data, on a way which is, uses this measure, which is still commonly used in finance, which is value at risk, and which basically will put a cap to the amount of leverage that you can put. But that cap you try to reach. Why? Because of what I said. Because the more leverage you are, and the more opportunities you have to make profit, okay? And the agents are all profit maximizers. So there is this target leverage strategy. And the point of the target leverage strategy is that it produces, and here will be very quick, it's very, very simple, but I don't want to spend too much time. It produces a positive feedback in the sense that basically when things go well, if you want to keep your leverage high, you are led to borrow more. You are led to borrow more because when things go well and your assets go from 100 to 101, your target leverage that in this example was 10, so the ratio between 100 and 10, it becomes less than 10. It becomes essentially roughly 9 because equity is raised to 11 and asset to 101. So you are led to do what? To increase by 10% as well your debt side, your liabilities, in order to get to optimal level of speculation. So if things go well, you borrow more. If things go bad, basically you start to divest. You start to sell assets. So you have, this is the engine which somehow in a market which is not ideal, but which has only finite liquidity and finite capacity, and moreover has impact of trading, because it's one thing if I buy a stock, when I buy one, and one thing is if I buy a million stocks or a billion stocks. I mean, it's a completely different impact on the market. The first is not noticed, so the price is not affected. But in the second case, you move the price. So there are there is this positive feedback, positive in the sense of system theory, which somehow tends to destabilize the system, and this is in some sense already following the intuition of the post-Keynesians. But here you really exploit the features of the market. So let's see a second why we then get this situation. The point is that regulation somehow says that banks have very limited choices in their behavior under stressful conditions. And this is conceptually the reason for which you can expect to have some determinism somewhere, okay? Because otherwise it would be strange that there is a deterministic skeleton in this stuff. At the same time, the point is that the fact that the market is has not infinite liquidity, and the fact that the action of the agents changes the prices, I mean, you impact the market, trading affects the market itself, is what creates a coupling between the dynamics of the leverage and the asset prices, with the idea that the dynamics of the leverage will end up to be the deterministic map, and the leverage and the asset prices will follow some sort of random dynamics, okay? So that's if you got this, I'm very happy, because that's basically the conceptual picture behind all what we are doing. Okay, so now there is the separation of timescales. Why? Because the agents we are interested in are immense, and their portfolios are also immense. So they cannot each day trade everything. So basically they trade continuously, trying to keep prices moved. They trade continuously. They try to keep the leverage to the estimate they gave. And then maybe every month or 2 months or 3 months, it depends. We will discuss this later. They try to rebalance the whole portfolio. They make a portfolio analysis. They compute the risk of their portfolio, and they try to make the new leverage target. They compute a new leverage target. So fundamentally, there will be now 2 time scales, an integer time scale, which is low, and which I will denote by t, and which is you can think of t as counting months or quarters. And then there will be a faster time scale, S, that you can think to be days or hours, it depends. And of course, then the little n, the bold-faced little n here, which is the separation of 2 time scales, will be how many days or how many trading periods you have in one portfolio rebalancing period. So it will be a number typically of the order of 100, okay? Roughly. It could be higher or slightly smaller, but the order of magnitude is around 100. Okay, I'm lost. Okay, then there is a little exercise which I skip of portfolio optimization, and there is a little exercise of looking at the impact of trading on markets. And when you make these 2 little exercises that I completely skipped, you end up with this model, which is the model I will discuss a little bit in detail. So let me explain this, and where lambda is the leverage. And this model, so this part above is, so we are not yet at the form of a noisy one-dimensional map. We are at the form where we have a 2-dimensional map, one for the slow variables, which are the leverage, and the second one is for the fast variables, which are the market returns. RS is a market return. And where phi is exactly what I wrote on the Blackboard, so it's the rescaled leverage which takes into account the liquidity. And then what happens is that the leverage is basically computed how? So omega is a memory parameter. It basically, it looks how much you take into account the past in estimating your risk when you are a bank. So let's think for a second of a completely myopic bank. So let's assume that the bank just looks only to the present. Then if it only looks to the present, this corresponds to choosing omega equal 1, no memory, memoryless bank. So each time it just looks to what happened in the last trading period. And then this formula becomes very, very simple. You can invert the square root. And it just says that the bank will do what I said before. It will impose a new bound on the leverage, which is exactly given by this, where this sigma p is the volatility of the portfolio which has been observed in the last period, and which is here the sigma hat, because that is actually the statistical estimator that you make from the observations in the previous period, in the previous quarter of the market, which is below, okay? And the omega there is actually what turns. So that would be a non-dynamical system in some sense. It would be a dynamical system which is totally driven by the market, okay? But if the bank is not completely myopic, if it has a little bit of memory, if it looks in the past, then omega is not going to be equal 0, is going to be something positive. And then what you do, you have to make an average. This is actually the same computation where you just make an exponentially moving average, weighted moving average between the observation in the last trading quarter or month, weighted with the past leverage that you had computed in the previous quarter, okay? So this is the thing. So the coupling between the autoregressive random process for the returns and the leverage dynamics comes basically through a statistical estimating procedure, which may depend on how much the bank looks at the past and which couples the two things. Okay, now you can reduce this in the form of the formula which I introduced at the beginning by basically making a sort of expansion, first order expansion. Okay, so the actual model I'm introducing is a simplification of the original slow deterministic, fast random dynamical system. Which is especially good, of course, when the separation of time scales is decently big, okay? Because I'm more or less just making a first-order Taylor expansion. And when you make the first-order Taylor expansion, you end up, as I mentioned it, with a one-dimensional map, which you can basically see the logistic map appearing. Of course, it's not exactly logistic because you have the denominator, but you see the phi 1 minus phi term which appears. And you have this additive heteroscedastic noise because the variance of the noise will depend on the position in a relatively elementary way. I mean, it looks complicated, but it's not extremely complicated. Okay. This is an example of a map. I mean, that's just a picture of one of our maps. And these are, for example, the effects. If you want, you can play and build the quantiles of the maps. You can just show how the noise, these are just different quantiles of distribution according to the noise of your map. So in blue, you have the deterministic map, which you obtain for noise equals 0. And here is the picture of the distribution of the possible maps that you are going to iterate for different quantiles, when n is equal 10, n equal 100, and n equal 1000. So of course, you do have a concentration of the quantiles on the deterministic skeleton, but as you can see, you still have, nevertheless, some sort of tail, okay? Because exactly because of the fact that you have this heteroscedasticity of the noise. And of course, this also puts a lot of technical nuisances. You are obliged to extend your domain of definition. You have to look at also at negative values. I mean, there are a number of things that are relatively standard in this business that you have to do because your system is not deterministic anymore. Okay, now let's concentrate a moment on the deterministic dynamics because I want to tell you the data analysis part, okay? I will show you a few statements of theorems, but I will not prove them with a traditional excuse of lack of time. So I will be so extreme in my traditional excuse that I will probably even skip the statements. But I mean, but you will see them appearing quickly. But I want to get to two things. I would like to get to the point where I show you how we fitted a real data set with our model. I mean, not the whole data set, but what the procedure we implemented to look at data. And then I would like to get at the end 2 minutes to say what we are doing now with Sandro, Fabrizio, and Matteo, and also with Marco. Okay. So when you look at the parameter space, it turns out that there is you can simplify your parameters and you can just use the memory parameter, which is omega, and then there is a fixed point phi star which always exists and which encodes the other parameters. So you get the parameter space can be described as a square. And fundamentally, the interesting region is the orange one, okay? Because in the two dark blue and light blue regions, you have either a stable periodic point or a stable period 2 point, okay? So that is less exciting, at least for us who are interested in deterministic dynamics a lot. This is a situation where you start to have a non-trivial invariant measure. So this is a typical portrait of what happens when you pick parameters so that you are in this orange region, which we call dynamical core, which is where you can have, you do not necessarily have, but you can have some positive Lyapunov exponent and some chaotic behavior. And then we know there are, I mean, a lot of classical results by Bloch, Lubitsch, and way more, of course. I'm just mentioning the general picture that you can keep in mind that basically somehow tell you that you can have in mind this picture of having either a periodic attractor or a counter attractor, or of course, for our purposes, the other case which is interesting when you have an absolutely continuous invariant probability measure. And of course, you can build, and you do build in a precise way the coupling, and you analyze the Markov chain with the attention that you have to truncate the noises. So it's not just a standard Gaussian or a standard uniform. You really have to be careful because somehow, as you see also from the original picture of the quantiles, the noise really depends on the position, and as you can see, it will shrink when you get close to the boundary, okay? So you really have that the noise part depends on the position, and that your kernels become a little bit nastier because you have all these truncations to do. Okay, anyhow, you can do all these things, and then, of course, in the end, you can prove, as I stated at the beginning, that you have finitely many ergodic stationary measures with BV densities, and uniqueness when, of course, you have either periodic or chaotic behavior. And finally, you can also look at the adiabatic limit, or if you want, when the separation of time scales goes to infinity, so when the little n which separates the time scales goes to infinity. And if you assume we weren't able to prove this boundedness, uniform boundedness of the density in n, then you can show stochastic stability and so on. Now, well, this is a typical picture of the deterministic map. Unsurprisingly, we see what we know. Here, the memory parameter has been fixed to be equal 0.5. So basically, you are making an equal average between the spot observation in the last trading period and all the past. Okay, that's the parameter of the exponential moving average. And this is, I think, exactly for the same slice with 1/2 memory, the picture of the Lyapunov exponent and how it becomes regularized by the noise. I mean, which of course provides in the end continuity for the Lyapunov exponent. Okay, so as soon as we have the noise, the Lyapunov exponent depends continuously on the parameter, and this is an illustration. Okay, I think I still have 10 minutes?
Yes, 15.
15? Okay, then it worked marvel just to skip all what I shouldn't have skipped, because now I can spend a few minutes on the data set and I can spend a few minutes on what we are doing now, okay? So we wanted to attract the attention of people in mathematical finance. And because, I mean, the message is there may be some dynamics, interesting dynamics to do in math finance as well, okay? Not just in mathematical economics, but also in mathematical finance. And one way to do it is to try to show that you can indeed read the data in a better way. Because this is basically what people in math finance and do. I mean, at least in the, well, not all of them, but those who look at the data, they try to somehow provide conceptual framework for encoding the data in a more effective way. They usually do it in a cinematic way, so that it's very agnostic. They look at the properties, statistical properties of the time series when it is time series, and then they say, okay, we may do I don't know, a mean reverting process, or we may do a process which has mean reversion for the volatility and just diffusion for the price. And so, but it's basically made by a sort of filtering of time series. And here it's a bit different because the dynamics has a few parameters, but not that many. And now we try to see if we can overlap our model to a real-time data set. What is the problem? The problem is that because of this heteroscedasticity of the noise, because of the fact that the noise has this structure, we cannot just use maximum likelihood, in particular because we don't know the portfolio rebalancing frequency. One thing we don't know is if in the data set we observe each point, or we observe only 1 point out of 3 or 1 point out of 4. We don't know what is the frequency of trading, but we only get the data from the frequency of reporting, which in our data set was quarterly, okay? So we have values of phi every 3 months, but we don't know if this phi that we see is t plus 1 or t plus 2 or t plus 3 or t plus 4, okay? We just don't know. So, and when you iterate this model twice, you immediately lose any Gaussian character because the transition probabilities are not Gaussian anymore. So there is no way to do it analytically, or at least we didn't find any way to do it analytically. So being in 2023, when we did this, 2022, 2023, we decided to train a network. We decided to train a network and to see if a convolutional neural network was able somehow on surrogate data to distinguish. So what is the training? You generate the dynamics and you feed the network without telling to the network if you feed the whole orbit or 1 point out of 2 or 1 point out of 3 and so on. And then you try to see if it behaves well. And it turns out that you can build just on Colab, a relatively simple network with a few layers, which seems to be able to get a decent identification, I mean, around 80–90% accuracy. And then you overlap these to real data. So what are real data? And here is the second part, which makes the thing extremely difficult and also to be handled with a little bit of care. Because the real data means a data set with 5,000 banks, but the time series are 60 points. So they are horribly short, okay? On the other hand, they are short, but as you will see in a second, the output is that 70–80% of those time series will just be either fixed points, noisy fixed points, or noisy stable periodic orbits. So if you have a period 2 periodic orbits with a little bit of noise, maybe 60 points, you can identify it, okay? You don't need billions of points. Of course, when we will proclaim certain things to be chaotic, that is a different story. It will be computing Lyapunov exponents on 60 points, but just to defend myself, this is standard in applications, okay? I have been playing a little bit with models in population dynamics in biology, just because of Jean-Christophe's work on rangers, on lemmings. And the data sets there are again time series with 30–40 points. And the population biologists compute Lyapunov exponents. So I mean, that's a world. Okay, welcome to the real world. I mean, the real world is a little bit different from what we like to imagine. Okay, we do this, and in the end, first of all, we discover that quarterly is almost never the right frequency. So typically, the large majority of the data set is made by banks that, according to our fitting, either rebalance every 6 weeks or rebalance every month. Okay, so I mean that's what is we observe. And so let's look at the two pictures separately and forget about the colors going from the left to the right. So on the left you have that the picture on the left should be compared with the deterministic division of phase space that I showed you before between regular and potentially irregular parts. So this blue is the code which tells that the orbit is in principle either a fixed point or a period 2 orbit. And the orange is where there may be some excitement, okay? And the the vast majority of the banks lie are blue in the sense that they lie in the part where the dynamics corresponds, the deterministic skeleton corresponds to something, some stable periodic point at most of period 2. But there is a certain number, about 15% of the sample. So as you see, the sample is not the whole thing. There is a 15–20% of the sample where the quality of the fit is so bad that we throw it away, okay? So we start from 5,000. We filter. We are left with around 4,300. And of those 4,300, we can make a classification. And in that classification, there are around 15% of the banks which are potentially in a dangerous phase space portion, I mean, or in a potentially chaotic area. And this is also the distribution of how many, I mean, if we, k equal 1 corresponds to the fact that the frequency of rebalancing would be quarterly, k equal 2, 6 weeks, and k equals 3, 3 months. Okay, anyhow, most of the banks in the dynamical core will have basically the k equal 2. And interestingly, we get a statistically significant result, which was interesting for, at least for the people in regulations, namely that the larger banks are more likely to have a chaotic leverage dynamics than the others. So this is, for example, and at least with the statistical accuracy that we can build from our sample, okay? So when you compare the statistical distribution of dynamical core and non-dynamical core, which are the two statistical distributions which are plotted here, in terms of the size of the bank, well, this slight different tail that you get is enough to justify the statement that I just gave. Okay, so in the last 2 minutes, 3 minutes? 5 minutes. Okay, I have to slow down. No, okay, I can spend 1 minute more on the last picture. Okay, so in the last 3–4 minutes, I want to say, I can first maybe summarize the results of the data analysis, and then I can spend 2 words on what we are working on now. So, well, actually, let me start directly from what we are working on now. So what we are now working on has 2 sides. I will mostly talk about the second. About the first, I will only say 1 word. We are finishing with Matteo, Fabrizio, and Sandro, a paper which has a tentative title of heteroscedastic noise. I don't know if we will really dare to send it with this title or not, where we overlay to our model a second possible source of noise, which is observation. And you may think, why? The reason is basically really inspired by real data, in the sense that, so what would be the observation in this model? It would be this leverage, right? So this data which are reported by banks, which say how big their asset size is relative to their equity. It's not at all uncommon or infrequent that those data are restated or are subject to possible different interpretations or plainly manipulated, okay? So the idea of overlaying to the observation of these noisy dynamics a noisy level of observation is rather natural. And on this, we are trying somehow to understand also to what extent we can apply, so that to use better the data analysis, some sort of filtering process, okay? So we would like to know if we are somehow able, nevertheless, to take conclusions about the underlying dynamics, in particular to understand if, for example, there is a potential instability, I mean, deterministic instability in the system or not, despite the fact that you may have this observational noise overlying to it. Second reason is the model per se. In doing this, we somehow forget about we don't focus only on logistic map arising from systemic risk. But there are a number of situations where you may have an observational noise which depends on the position in phase space that you are. At the simplest level, in a completely different setting, in astronomy, if you want to understand if an asteroid is aiming at the Earth, when it's very far, the uncertainty on the position is going to be much bigger than when it's closer, just because it's fainter. So I mean, the fact of having a position-dependent observational noise is common in many, even celestial mechanic applications. The second is more trying to refine the analysis of systemic risk, and it's a work of Marco in his thesis, which is to say, okay, until now I haven't justified it to you, but I've described the system where there is one market and one financial institution. Okay, that is a little bit too much, right? The markets there are more than one market, and certainly there are more than one financial institution. So the first thing we are starting to play with is just to say, okay, what if we have two banks or n banks, let's say two for a second, and if they both trade the same assets, so that the autoregressive process below is obtained by fundamentally making a weighted average of the leverages of the banks. So the I is the index of the bank. The market is only one. So you have n dimensions for the banks and one dimension for the market. Actually, you could make an autoregressive process with more variables, but let's stick to the simplest situation. And you just proclaim the autoregressive coefficient to be a sort of weighted average of the leverages of the various banks. Each bank will do the same game I've been telling you with its own memory. And then what can one say in this situation? Are there new phenomena coming out? It seems that there are some interesting things which are coming out. This is an example where you just have two banks with equal weight, but two different memories. And you see that there is a sort of little emergence of an Henon-like structure in phase space. So this is what happens when, you see, of course, the memories have to be decently far from zero, otherwise you are completely myopic. So one is 1/2, but the other one starts to be a little bit more myopic, as 0.3, and then there is a little bit of emergence of this. We've just started to analyze, I mean, and we will keep working on this, but I hope there will be something interesting coming out. Thank you very much.
Thank you, Stefano, for the very interesting talk. Is there any questions?
I have a rather naive question and then another one which is a bit more technical. You said in the beginning that the Markov chain associated to the slow-fast system, under certain assumptions, you can prove uniqueness of the stationary measure, and from this you get eventually central limit theorems. And my question is, from the point of view of applications to finance, what kinds of limit laws they care about? I would imagine
all of them.
All of them, including.
I think if there is a real business, it would be. I think it. Okay, there has been a lot of people coming from physics and nonlinear physics looking to finance in the last 20, 30 years. There is even a branch which is called econophysics. You may think what you want about it, but there are some things inside it which are interesting. So, for example, there are a lot of people who applied multifractal analysis to financial time series. Legitimately, first of all, the fact that financial time series are not normal or log normal, they're really not very well stationary and so on, it's known since the 40s, the 50s. Even Mandelbrot himself really did something in that. I mean, it didn't just... he really wrote papers on this, realizing and making, and then he started building models just maybe with iterated function system, which look a little bit too naive. But in general, the fact that there is this aspect of distributions, statistical distributions, very rich in this problem is a fact. Okay, what I think is that there were people looking at dynamics in finance at some point, which was to some extent too early, because the first wave of people who tried to look to some problems in finance with dynamics came immediately after basically the Ismail, the 60s, and they didn't have even understood the importance of ergodic theory. So they went to the subject with the bifurcation tools, but basically not with the ergodic theory. And this is really a pity, because the most common denominator of people who look at data in finance is econometrics, and the econometricians are first cousins. They're really first cousins. I mean, they are the people who do ergodic theory of processes which are sort of, I don't know, linear, or they make very sophisticated things with different tools, but they're really first cousins of people in dynamical systems. So I think there is interest now in looking. So all possible, sorry, it seems a general answer, but I think the answer is basically all of them. So in our case, of course, we were concentrated on the central limit theorem for the leverage, okay? So that was what we wanted to do. But it's just one little drop in a big sea, which I think deserves to be investigated by us.
Okay, thank you. Can I ask another one? The other one is, you said that when the noise is not Gaussian, that epsilon t, you don't have tools. My question is, the Markov operator associated to the system is not quasi-compact anymore. What happens? Why is it that you don't have tools anymore?
So, I mean, we couldn't find standard theorems fitting our framework. So we had to reprove them. This is what I meant. So, for example, we don't know recurrence properties of our chains, if the R is recurrent. This we don't know. So you do then what you can, bit by hand. But I mean, you cannot, I mean, we spent some time, Sandro spent a lot of time, he's very serious, a lot of energy, trying to see if if we were missing something. We asked around, and it seemed that the best thing to do at some point was to redo it ourselves.
Are there any other questions or comments? If not, let's thank Stefano again.